Hello, welcome. Lecture 40 here today. So, we are going to continue discussions on LDMOS. It seems like we will also need one more lecture on LDMOS. So, we will spill over the discussion of LDMOS to lecture 41 also. After that, we will start bipolar devices from lecture 42. So, today in lecture 40 we are going to continue from where we had left, which is basically which introduced the operation of the LDMOS, VDMOS. And we looked at the different layers, how the current flows, the blocking voltage, advantages and disadvantages, etc. We are going to talk about further things, especially in terms of the breakdown on resistance and hot carrier injection. In today's lecture, we will talk about the parasitics, which are a necessary evil in LDMOS. Okay, so over to the whiteboard here. So what you see here is basically a schematic of the LDMOS device with representative parasitic components that are listed out. So gate resistance is a significant parasitic resistance, and polysilicon gate is not the best, that is why people use silicide also on top of that, which is something already I discussed. CGD, the gate to drain coupling capacitance, CGS, the gate to source coupling capacitance, very important, these are extremely important parameters. This is a necessary evil, the drift region blocks the voltage, the VBR actually drops here, it is a 2-dimensional profile, but anyways the gate drain spacing largely determines the breakdown voltage. So, the resistance also comes because of that. So, this is a necessary evil, the drift region. Okay. Drain to source capacitance, it matters, but it is a little second order effect, you can say, the drain and source, because this is the source. Okay, there is no body here separately. So, the drain to source coupling, it is lightly doped p type epi, this p type doping is lightly doped. So, this drain source capacitance can be very small. Okay. Source resist, this is the resistance of the sinker. Because the p type sinker is this is an implanted highly doped region. So, if I look from top to bottom, I should see a very low resistance path. So, you see here on the y axis the doping concentration, x axis is the distance from the top to bottom. The dotted line is not a good one because the doping has reduced significantly and come up, it has gone to like high 16s, it is pathetic, it is bad, okay. It is very bad, you can see this is bad. It is a low doping, which means this part, because this p type substrate, this is the p type substrate, this is the sinker to substrate link, which is this, is very low doping, and so this is a high resistance path. This can be detrimental to your device performance. The top one here, okay, the top one here is a good one, this is a good one because the linkage here is still around 10 to the power 18, right. So, that this part is should be highly conducting or as less resistance as possible, because you are going to implant that and you are going to also anneal, you do not want the substrate out diffusion to consume the background epi that I had already talked to you. Okay. These parasitic resistances, all these different parasitic resistances, they will dissipate energy, they will reduce your peak power performance. Okay. They can also affect your gain, gate resistance can significantly kill your gain. Okay. Your efficiency, your gain, your knee voltage, everything is going to be dependent on the resistances. And what about the parasitic capacitances like CGS, CGD and all other capacitances? Capacitances affect the small signal performance, FTF max. If your frequency performance becomes lower or poorer, you are going to get a lower power or lower gain at a given frequency. So, you have a cutoff frequency of say 10 gigahertz, how much power can you get at say 3 gigahertz? Very low. Okay. You need to have a cutoff frequency of say 20 gigahertz, in that case you are going to expect a good power or gain at 3 or 4 gigahertz. So, cutoff frequency can be really affected by capacitances, okay. It can even completely kill the cutoff frequencies, please remember that. So, a very simple expression for FT, of course we have discussed this many times, so I do not want to repeat that, GM by CGS, okay, and it basically it is the intrinsic FT and it directly depends on the velocity of saturation. So, your GM should be high, CGS should be low, Fmax depends on this, this is actually R out by R in, but in general it should be gate resistance below. So, the gate resistance should be as low as possible, and this is the output impedance actually, the output channel resistance. So, you can say the inverse of output conductance. So it should be the output resistance should be as high as possible, which means in the IV the saturated curve should be as flat as possible, this slope should be as close to 0 as possible, then 1 by slope is infinity. So, that R out is infinity, so that Fmax will be like not infinity, I mean as large as possible is better. Okay. Now, the question here is the critical capacitances CGS and CGD, you can talk about the intrinsic device only. These are very much dependent on the voltage, the drain voltage, also of course on the gate voltage, but they depend very much with gate voltage and drain voltage. So, when the gate voltage and drain voltages change, this capacitance can change or will change, and because these capacitances will change non-linearly, what will happen is that they can affect the signal, like they can distort the signal. So, the gate bias will define the class of operation, class A, class B, the question point, the Q point, but the drain voltage can change. So, in a output swing, the drain voltage can go from 28, the mean of 28 volt, it can go up and down. So, when the drain voltage swings, the capacitance CGS CGD also will change, and if that changes, then 1 by omega CGS or 1 by omega CGD are also going to change. That is a headache, because the matching of the amplifier, when you match the amplifier, when I say match, we mean the impedance looking into the load, conjugately matched to the output impedance of the device. The impedance matching happens for a specific frequency. Okay. When your capacitances keep changing with every cycle of the RF, your matching conditions can change, and that is a headache. So, nonlinear modeling is very important. People do a large signal nonlinear model of this device. For that, people use pulsed IV in conjunction with load pull data. Load pull means that you are going to measure the output power, you are going to measure the different, you tune the load, you find out the different impedances, okay. And from pulsed IV, the behavior of the device and the pulse condition. People use transient and thermal effects also. They do large signal modeling, and that is very crucial in actually getting the amplifier, the designing the amplifier, output matching and everything, okay. So, this nonlinear dependence of capacitance is generally a worry, but that is something unavoidable. So, what I am showing you here? I am showing you here the drain source capacitance, okay, with respect to the voltage, the drain voltage. It varies nonlinearly because this depletion, the gate and the drain and source, the depletion will extend, the field will penetrate further when you apply higher voltage. So, this depletion between the P type and the N type, the depletion region here is going to change when you apply voltage, the drain voltage here, and that is why there is a nonlinear dependence of the capacitance. Here I am plotting here is CGS, the input and CGS is like the channel, the gate to channel capacitance, you can say, and the gate to channel capacitance, this, if you recall your classic MOS capacitance from your undergrad textbooks, this is a shape that you get, like something like that. So, that is a classic MOS capacitance, inversion, accumulation, depletion, etc., etc. So, that is going to be nonlinear, okay, and typically this CGS is 2 to 4 times higher than the CDS, okay, and CGD, the gate drain, which I am not showing you here. Gate drain has the same shape as CDS, because the gate drain is this capacitance, the coupling between the gate and the drain, it has the same shape, but the magnitude is much lower. Gate drain CGD can be much lower, it is around 5% of this. So, it is much lower, and that is because of this shield. This shield, this creates like a Faraday cage. So, the field lines will terminate, and it will not be able to, the drain field lines will not be able to reach the gate, and that is why the gate drain feedback capacitance can become very low, and it is not so much of a worry, because higher CGD can reduce the power gain, but the fact is that there is a nonlinear dependence of the capacitances on the drain voltage at a given fixed gate voltage, and these nonlinear capacitances have to be taken into account while matching, while designing the amplifier, because otherwise it can lead to distortion in problems in matching and things like that, okay. So, that is something very important. Now, let us take a careful look at different capacitances. The total gate source capacitance, if you look carefully in this structure, the gate to source capacitance is the intrinsic gate to source capacitance, maybe I can use a red color here. The intrinsic gate to source capacitance, coupling between the gate and the source through the oxide, and of course any depletion region that might form, okay, which is this, plus GBO, this is the gate to channel coupling capacitance. There is an inversion channel forms, no, the classic MOS cap. So, there is a coupling there, it is parallel, this and these are parallel. So, they are adding A plus B in a way, okay. And the third is CGFP. What is that? This is the source field plate that is going around this. So, the gate metal to the source field metal has a capacitance here that is going to this, and these are all parallel, that is why this is the total gate to source capacitance. Now, okay, I will remove that. Now, what is the gate to drain capacitance? So, gate to drain capacitance, this is gate this is drain. What are the capacitance? CGDO, this is the intrinsic gate to drain coupling, of course, right. And in parallel you have two capacitors in series. One is that this gate is coupling to the source field plate metal, which is coupling to the drain here, because this is the drain extension. No, this is the drain is connected here, right. So it is connecting to the source which is connected in series to this. So this CGFP is in series with this capacitance, which is CDFP, the field plate and the drain drift region. So the series of this is this, which is in parallel to this, that is why this. So this is your CGD. And finally drain source capacitance is this, which is the intrinsic so the drain and the p-type epitaxial layer capacitance plus this. Why? Let me remove the annotation maybe. You see the drain, this is entire thing is drain, the drain drift region, right. So the drain is coupling to the source, this is source by the way, this is source. So the drain is coupling to the source through this, okay, which is CDFP, and that is in parallel to the drain source capacitance. This is also connecting to the source here, this is also connected. So this is the drain source capacitance. As I said, the gate is shielded by the source field plate, which is wrapping around in a way over the dielectric, okay, and this helps prevent hot carrier injection also by reducing the peak field, okay. Otherwise the hot carrier injection can significantly degrade. Everything else is fine. I have talked about everything, but this is the way the capacitances are calculated, or you understand the capacitance split of these different capacitances in the LDMOS, okay. Now we come to the breakdown RDS HCI. These three quantities are very critical. We have already talked about them to some extent. BVDSS by nomenclature is defined as the breakdown voltage when the channel is off, which means you keep the gate voltage at 0, so the channel is off. It is an enhancement mode device, which is a good thing for many applications. So it is an enhancement mode device, you keep the VG at 0 and you go sweep the drain voltage. At one point the drain the buffer will break down, that is your breakdown voltage. RDS on is the on resistance, is the reciprocal of the slope of IV in the linear region, IV, IDVD, you have this, no, right. So this slope, of course the slope keeps changing with gate bias, so you have to define this at certain gate bias is your on resistance. HCI means hot carrier injection. Hot carriers are the carriers that have significantly higher energy, much higher than KT in a way. So the significantly higher energy, okay, they kinetically they are accelerated by the high field, and because they are going to be accelerated high field, because this region has a very high field, this region. So the electrons that go are very energetic, they go in a very high field, they can get misdirection because of the high field, they can scatter and they can either go to the oxide here, there is an oxide in this part also, or they can go to the oxide below the gate. Depending on where they go, these hot carrier electrons they can lead to different reliability problem. The most vulnerable structure here is the gate drain part, highest peak field comes here, another peak field comes here, okay. So what is happening is that at high voltages on the drain, say 28 volt, you may not be at the avalanche, you may not initiate impact ionization, so your device is not breaking down. However, the field is still very high, that electrons become hot, which means they are highly accelerated, they have sufficiently high kinetic energy, and they have the probability of entering the field oxide or the oxide below the gate because of the high energy, they can actually get scattered and enter, okay. That is a reliability concern. I will come to the hot carrier injection again after we discuss some of the other issues, but that is the basic gist of hot carrier injection. We will come to the perils of hot carrier injection in a later slide. Now this drift region has a certain depth, by the way, this is a certain thickness, say xj, the junction depth, that depth and the doping here ND maybe. So that ND in per centimeter cube into the junction depth in centimeter is basically per centimeter square. This is the dose, this is the dosage of the doping that you have used in the drift region. This is very critical, extremely critical. The length of this also is extremely critical because this affects the on resistance and the breakdown trade off. This is, we have done it so many times, okay. Field plate we have already talked about, and for this thickness has to be also as thick as this at least, because the fields will penetrate. You do not want the field to reach this p type p plus, because it will break down. So it cannot be very thin, okay. And depending on the device, this design, the sinker need to be designed, because you want this maximum conducting, minimum resistance part here, okay. Now a very important thing here is RESURF. I will come to that. RESURF helps improve the breakdown field without compromising the on resistance, and it is unique to silicon devices, very hard to implement on a 3.5 device, okay, because you need a p type layer below, which is not there in a 3.5 device, okay. Why is there no p type layer on the 3.5 device? You should try to answer yourself. In a gallium arsenide MOSFET or a pseudomorphic HAMT or a gallium nitride HAMT, why is it very hard to have a p type layer below the channel? What will be the problem, okay? You have to think about it if you really want to understand the technology. I'll answer that question maybe towards the end of this course, but it's something that you want to ask yourself. Why is it that in silicon we have these p type layers very easily, it's routine, but in gallium nitride or gallium arsenide having a p type dope layer can be very difficult. Although in gallium arsenide people do use the p type layer, but RESURF is still very hard, and in gallium nitride it's even more difficult, okay. Now on resistance, I already told you the inverse of the slope. I already told you want the on resistance to be as low as possible, because it affects the knee voltage. You see, if this is your IDVD, this is your knee voltage V knee. You want the knee voltage to be as low as possible, because that defines your output swing. If your knee voltage is here, then your swing can be more, correct. So your knee voltage defines the RF swing also. Your knee voltage should be as low as possible. To give you a feel, handheld mobile phones use an HBT for instance, where the knee voltage is like 0.5 volt or 0.7 volt, it is crazy, okay, knee voltage. Gallium nitride could have 3-4 volt knee voltage. Again the knee voltage depends on the breakdown. If you want a very large breakdown, then your knee voltage will suffer, because you will have a large gate drain spacing. This spacing will be large and your knee voltage will also be poor, large matlab, knee voltage will be large. Okay, so this region is the largest. This region is the largest contribution to RDS on, which also has breakdown. This has been told infinite times, so we are not going to repeat that again. As I also told you, this p type lateral diffusion should not reach the n type drift region, otherwise it will overcompensate and create a dead area here, where p type and n type have compensated each other. There is no channel, it is off, and the gate has no control because it is outside the gate. So it is a permanently or an ever off transistor. Okay, so you do not want to do that. So diffusion, lateral diffusion is very critical, which means your thermal annealing, everything is very critical, okay. Now this is the concept of RESURF, and this is something very important. Maybe I will explain the concept of RESURF with a whiteboard, and then I will come to the image that I am showing you there. The basic concept of RESURF is like this. So suppose you have a highly doped P region, and then you have a relatively lightly doped N region. Then this p type region does not matter, because matters in the sense that the field will not drop here, the field the depletion will only happen here, correct, and the field will only drop this side, a negligible field will drop on the other side, correct. And you keep applying a voltage, you apply a voltage, the field will keep increasing, the depletion will keep increasing. At one point the field will reach something like that. This is your critical electric field, F critical. The moment it reaches that critical field, the device breaks down, and this is not high school physics, this is undergrad, your standard device physics. So the area under that curve is your breakdown field, right. Fair enough, that is how it is, that is how it is, and as soon as this critical field is reached, you cannot do anything about it, your breakdown happens, inevitable, great. Now the funda of RESURF is that you have this n minus drift region, or a relatively lightly doped region, and there is a p type region here. Imagine that there is in a perpendicular direction there is a p type region here, it is not p plus, it is a p region, the doping of p can be adjusted, it can be anything. So what will happen is that, maybe I use a different color here, your voltage is always going to be applied here, by the way, here. However, because this is connected to this is also grounded here. If this is grounded, the p type is grounded, and this is drain here, the drain is coming here. Okay, so essentially you are applying a high voltage on the drain, say plus 10 volt, plus 20 volt. So if you are applying a high positive voltage on the n minus drift region, and there is a source and plus source of course, and so p type is grounded, what happens to this junction? this junction becomes reverse biased because the p type is grounded and n type is subjected to the n type drift region is subjected to a higher positive voltage. So, it is a reverse biased junction. So, because it is a reverse biased junction, the depletion will extend on both sides. The more you apply the drain bias, the more this depletion will extend on both sides, correct. The more they have depletion will extend. This is much thicker by the way. So, you do not care about the depletion on the bottom side, okay, it is much thicker than the top and well. So, what happens is that it is depleting on both sides, correct. However, what? However, your lateral depletion also extends this side. While you are applying the drain bias more and more, not only is the vertical junction depleting, the lateral junction is also depleting, correct. The lateral junction is also depleting both. So, there is a orthogonal depletion that is happening, correct. There is a depletion from the bottom PN junction you are depleting. There is also depletion from the side, the left side also you are depleting, both depletions are happening. Now, what is the funda of RESURF? The funda of RESURF is, yes, you understand, right, both sides are depleting. The funda of the RESURF is that this n minus region, no, and then you have a p plus, and suppose you have a thick p here, okay, such that you have depletion here on both sides. The funda of RESURF here is that before this lateral junction depletion reaches the peak electric field, before this lateral junction depletes it to the maximum possible, before that happens, the vertical junction depletion region should deplete it completely, okay. This is entirely depleted. Of course, there is a thicker p type, so the bottom does not matter, but this entire n region is vertically depleted. The entire p region from the vertical junction, it is entirely depleted. It is entirely depleted even before the lateral depletion has reached its maximum that it can reach, or in other words, before the lateral depletion has reached the critical electric field, because the field here will reach the critical electric field, not the lateral one here. Before this has reached that, the vertical junction depletion has depleted the entire n type region. So, you have an entire n type fully depleted region is fully depleted because of the vertical junction, and then there is a p plus here which is starting to deplete, but this is already depleted. So, if the n type region is fully depleted, then this lateral, in the lateral direction, you do not have to expend effort in depleting the mobile charges or in uncovering the mobile charges, I mean the ionized impurities. You do not have to put an effort to deplete the carriers because they are already depleted from the vertical due to the vertical junction depletion. So, the lateral field, because they are already depleted, no. So, the lateral field, instead of looking like a triangle like this, it will look like this. It is a constant field because it is fully depleted, it will look like something like that, okay. So, the area has increased, the breakdown has increased, and it is still not reached critical field. I will repeat, your lateral, in the lateral direction, you do not have to spend energy or effort in depleting the carriers anymore, because in the vertical junction has already depleted them, which means the lateral junction you can keep applying voltage and still not hit the critical electric field because you are not depleting, it is already depleted. It is an already depleted semiconductor where instead of n minus it is like an completely depleted semiconductor. Think of it like an intrinsic semiconductor. You are going to increase the voltage on the lateral direction, but your critical field will come much later. The value of the critical field does not change, but you are not going to have and spend any energy or effort in depleting because it is already depleted. You see my point? So, for a RESURF, the funda here is that, maybe I will just go ahead with the so that is what, this is the vertical depletion. You want the vertical depletion to happen completely before the lateral depletion kind of reaches the peak electric field. This is the peak electric field. So, in the lateral direction, in this lateral direction, the peak electric field is like that and it is straight, it is not a triangle because it is depleted fully. You see, this is fully depleted because of the vertical field. The vertical field looks like this, it is a triangle. It is a triangle because this is p minus, this is n minus, kind of equal doping more or less. So, this is a triangle. okay, and this is the area, it is fully depleted, but you are not going to break it down here at this junction, because you are still going to apply voltage and you are still going to get up to that point. So, your eventual field will break at this point only. The area under this is much larger than the area under this. However, your on resistance has not suffered because it is the same well. This is the off state condition. In the on state, the same well will conduct. So, your on resistance does not get affected, but your breakdown voltage improves significantly. This is an amazing concept called reduced surface field or RESURF. Okay, it is an amazing concept, it is reduced surface field or RESURF. Now, forget the equation here, maybe I will I will just not use the equation here. So, what I can do here is that qualitatively, if I can tell you the equation without writing the equation, then the understanding becomes easier. So, what is happening here is that suppose this is your thickness of the N well, which is xj, the junction of the N well, as in the N drift region, okay, fine, and this is your P plus and this is your P. So, this P has, this doping does not matter, this doping is suppose Nd and this doping is suppose Na, right, this doping is Na. Now, this doping does not matter. So, if you just consider the lateral dimension, you know the doping Nd here, you know the critical electric field, say I will call it ECR, then the maximum I can express the maximum breakdown voltage I can get in this junction, the maximum voltage I can get in this junction, the VBR in the lateral junction I can apply between this, the maximum voltage that I can apply as a function of the critical electric field, as a function of the dielectric constant of the material, right, and as a function of doping. These 3 parameters I can express the breakdown voltage very easy, okay, that is what is done in the next slide precisely. This is the breakdown voltage that will happen, okay, without considering any RESURF. Suppose this breakdown voltage happens to be suppose 50 volt, suppose at 50 volt, just giving an example. Now, the lateral in the vertical direction, in the vertical dimension, for RESURF to happen, okay, at before hitting 50 volt, before hitting the breakdown voltage, I mean before hitting the breakdown voltage, the vertical depletion that happens, no, the vertical depletion should completely subsume or consume of this entire depletion, entire and the depth, okay. So, because the depletion is on both sides of the PN junction, you know there is a depletion on the N side, there is a depletion on the P side, the total depletion of the N plus P is something like 2 epsilon naught epsilon S by Q VBI built in voltage plus V, the voltage that is dropping, the reverse bias, into 1 by Na plus 1 by Nd square root. This is the classic thing, but this is the total depletion. So, we can express now the depletion only on the N side, we can express the depletion only on the N side here. The depletion on the N side, the maximum depletion that can happen is the junction depth, okay, which is your this is your maximum depletion that can happen, right, which is this essentially this, okay, this is this Nj Xj, okay, that is the maximum depletion, the drift region, the well. So, the maximum depletion that can happen there, and you can ignore the built in voltage because the built in voltage will be like 0.7 volt and breakdown is like 40 volt 50 volt, so you can ignore that, okay. So, this voltage is your this voltage. So, if you apply, you do not put 50 volt, you put the expression of this breakdown voltage in the lateral direction. If that voltage expression is inserted here, and that is the total depletion you will get, and as a function of the depletion you can express the function of the depletion on the N side, this should be completely depleted, okay, before that breakdown happens, okay, before that breakdown happens this should be complete. That means this junction depth should be less than equal to the depletion that will happen because of the vertical depletion. The vertical depletion should be more or equal to the junction at the breakdown voltage, before the breakdown voltage happens, okay. So, what you do is that in the lateral direction you first find out the breakdown voltage as a function of the doping, as a function of dielectric constant, as a function of the critical electric field, which is precisely this. Here N well is your Nd actually, the doping in the well, okay. So, this is your breakdown voltage in the lateral direction. Now in the vertical direction, the depletion on this side the depletion on this side is this expression under square root. It is a classic semiconductor equation, now no fancy. Okay. P sub is your doping here Na, no, okay, assuming this substrate is not the P plus substrate, by the way, this is the P plus the P epi actually, this is how do I say, this P epi, this is the P sub that they are saying, okay, not this, okay. So this is P sub, this N well is Nd. So this expression V applied is the reverse bias voltage you are applying in this junction, which in this case I will use as this, because that is the maximum. I am applying a voltage between the gate and the drain only, which is also getting converted into the top down voltage, by the way, because this is shorted to the substrate below, that is why, okay, but this is the same voltage actually, voltage is voltage. So this breakdown voltage I am substituting here, and this is the depletion. This, the condition for reserve is that this depletion should happen, should be more than that means this entire region should be depleted, max depletion should happen before we reach the breakdown voltage, that is all. If you do that, you get this is basically the product of the drift region into xj, the dosage, it is per centimeter square of charge. The doping times the thickness of the drift region will be less than equal to 2 into 10 to the power 12 per centimeter square, by the way, into square root of p type doping of the epi divided by p type doping plus n type drift region doping, the n drift region doping. Okay. This is a very important expression, and it basically tells you the dosage, the product of the doping of the drift region and the junction depth that is required to enable a resurf action. If you have a lower dosage than this, that means you are not able to reach the complete depletion, your breakdown will happen early, okay, correct. And if you have a much higher dose than that you need, maybe the junction depth is xj is very thick, then this will not be able to deplete it completely before this sidewise depletion reaches the maximum. So there is a sweet range of this over which you can actually get the resurf action. So this is precisely plotted here. This is breakdown voltage on the y axis, and this thickness of the resurf action, you can say the thickness of the resurf action is the thickness of this well, the n type drift region, okay, so that I am not going to confuse you again. It means this is your junction depth xj, that thickness is this y axis x axis, it goes from 0 to 4 micron, and this is the breakdown voltage. You can see that the breakdown voltage without any resurf action will be like this constant. Now with resurf action the breakdown voltage is very high, but it keeps coming down at higher thicknesses. At very high thicknesses you will not get any advantage because the dosage is too high, either the doping is too high or the junction is too high, such that the vertical depletion is not able to fully deplete it before the lateral breakdown happens, that is why you are not getting any advantage here. And whenever the thickness is too low, this thickness is very low, then this vertical depletion quickly happens, but it is not sufficient that the lateral breakdown will happen prematurely now, because you could not have prevented the lateral breakdown anyways, okay. So that is why this is a premature breakdown region. This is the region where you are going to get the benefit of the resurf. You can see the breakdown has improved, okay. The breakdown has improved from something like 50-55 volt to up to like 75-80 volt at the best case, okay. So this is the concept of resurf, but now people adopt double resurf, triple resurf from the top, there can be a top p type also, by the way, there is lot of designs, by the way, to improve the breakdown. So this is the concept of breakdown on the resurf, okay. So with that we will end today's lecture 40. We will have one more lecture to go where we will talk about hot carrier injection and reliability aspect, multi-finger device layout, manifold. We will talk about electromigration reliability, and then we will quickly go through some commercial examples of LDMOS devices and how they are or where they stand with respect to the rival gallium nitride technology. We will do that in the next class, lecture 41, okay. So thank you for your time, I will see you on the next class.